Okay, thank you very much and welcome Cal to the stage.
Okay, hey, thanks for having me. I'm just gonna go over kind of like the basics of FHE, sort of how the pros and cons of different privacy technology, etc. So yeah, just jump right in and how to build using just native Solidity. So from a high level, fully homomorphic encryption. I don't know if you guys have heard of this before. Like fully homomorphic, kind of like homo is in like like a homosexual, like when a man likes a man. So it's kind of like you think about it like one to one, sort of like same, I guess, in some aspects. So basically, what you do with plain text should happen to the ciphertext. So fully homomorphic encryption is basically the ability to run operations on data without having to decrypt it. Generally speaking, usually when people talk about like some sort of security, usually you're kind of just encrypting it. You might encrypt it locally, client side, whatever, and in transit it might be encrypted. Except when you want to run these operations, when you want to do lookups, etc., queries, it can be difficult to do these type of like drilling into these whatever if you don't actually know the contents of what you're drilling into. So if you can see here, basically you're running an encrypted function. What's an encrypted function? But let's get into that a little bit. So really high level overview, if you just think about like a simple example of a basic encryption scheme where you have a generation of a private key and a public key, secret key, whatever nomenclature you prefer. So basically you will encrypt this message M towards a specific pub key, and then that specific pub key will be able to decrypt it. So this is pretty straightforward. Won't spend too much time on this, but fully homomorphic encryption is basically adding one extra step here, where you have the generation, the encryption, the decryption, but you also have an evaluation step. So if you look at it in terms of like you have the like normally when you encrypt this message with a pub key, and then you run a function on top of it, the evaluation is going to be done homomorphically, and then you can decrypt as you normally would. This should be basically the same thing as like running a function on this message M. So that was just a convoluted way of saying like if you want to encrypt the number 5 and then you want to run a function that will like double the number 5 or like take another number and then run some arithmetic expression on top of that, you can do that without decrypting. So you can do like 5 times 5 without necessarily revealing what the values are or what the product is in this case. And so it's relatively straightforward too if you think about like where's this computation happening. It like when you're running a function, you can run a function on this encrypted value, and it's still going to evaluate to what it should evaluate to. And so the communication is client side only. You can use some sort of like zero knowledge proof of plain text knowledge, for example, to verify that the construction of the ciphertext and that it's formatted correctly, etc. And the computation in this case is slow. I mean, just FHE operations. But in the blockchain space, you can think of this as like the server side is going to be the blockchain, the machine that's the virtual machine or whatever that's running the logic. So when we think of this FHE nonsense, basically you think homomorphic encryption has existed, but the concept of fully homomorphic encryption means that you can run arbitrary operations on top of it, which theoretically makes it something that you could build out your state with and use for a lot of different things. And yeah, so buzzwordy in some aspects. I kind of think of FHE as sort of like sort of what we thought like ZK was going to be for privacy in some aspects, in terms of like being able to run things on some sort of state. I mean, I'm dealing with a really broad brush here, but mostly I'm just kind of talking in the aspect of like where privacy is kind of going to go, and we're going to go into the details about this a little bit more in the next slide. But if you think about like the history of this, it's not like FHE is like a new concept. I mean, it is kind of, but like the idea of privacy homomorphisms have existed, since Seminal works released in the 70s, etc. And a lot of work was done in the partial homomorphic encryption, which kind of earlier when I was talking about the difference between fully homomorphic encryption is that it kind of has this concept of like keeping the ciphertext like. FHE uses noisy encryption, right? So it's kind of like when you obfuscate the truth with some like bullshit. Kind of like when you're playing like poker or something, you gotta bluff sometimes so that people don't know. Like if you're just playing it straight up, every time you go in, someone's gonna know you got the nuts. They're gonna fold. It's not EV, right? It's not good EV. So sometimes you gotta bluff. You gotta bullshit. So there's a bunch of different schemes here that diverge. I won't go into too much detail. If there's any questions, I can talk more. But yeah, basically the main two branches here, if you look at it, it's a fast bootstrap branch, which uses like Boolean circuits, which is kind of good for like the deterministic state for things when it comes to like verification, etc. But there's also level schemes, which are kind of approximate use float. And some people speculate that this is like, I guess, ideal for things like machine learning, etc. But yeah, anyways. So yeah, here's just kind of like a high overview of like some different schemes and how they diverge. Again, I would love to talk more about this, but for the sake of time, let's just move on. Okay, so from a high level, when you think of like, I'm sure a lot of us are familiar with conceptually with using zero knowledge proofs for privacy in the space, which is very like the way I see it is like zero knowledge proofs are very good, especially in a situation where like the inputs of them can't be encrypted. Like if it's a plain text, like if you're pulling it from your email, if you're trying to like verify your passport or something, or do some sort of check, it could be very useful. The issue here is that if you want to have like a shared composable state, it starts to get difficult because if you have adversarial inputs, they're going to lead to the prover, and so if that makes sense, it's kind of good for. It's very good for like single use. Privacy cases, like I said earlier, we use them for like the ciphertext formation. But the issue here is again the composable state. So with FHE, basically you can have these different like inputs for things and allow people to keep them private and advance the state that way. So you guys also might be familiar with like multi-party compute, multi-party computation. And in some ways I think this is probably the most similar thing to FHE in terms of like when the data is secret shared, so you can actually run these operations without having to decrypt. The issue here is that if you look at the kind of the formatting, it's gonna be communication bound, which is always gonna have I guess some sort of like overhead in the case where like what do you do if one node goes down? Are we just fucked? So I mean, it really depends how you set up your scheme, but basically the main thing to keep here is like when it comes to using FHE or MPC for shared composable state, it kind of comes down to the communication and the interactive nature of it. And also you can use MPC for threshold decryption, but again we'll get to that step a little bit later. And so here's kind of an example when you also compare it to something like a TE, for example, like SGX, which is, I guess these secure enclaves are going to have some sort of like known attack vectors, and they're not necessarily like, cryptographically secure. But the main thing I just want to highlight here again is just the interactive nature between homomorphic encryption and multi-party compute, just in the case that like in some aspects it's easier to parallelize. Which can be good for scaling. But like I said, you can use it for threshold decryption, so you turn this interactive feature into, I guess, like a feature, not a bug, if that makes sense. So you use the nature of it that it requires this round for actually some sort of like key construction or secret construction. And yeah, just to summarize, kind of like TE's fast programmable, they're kind of sexy right now. There are known attack vectors, etc. Maybe I'm just like doom larping it, I don't really know, but like, it is what it is. MPC also kind of similar again, but has the communication bound. And ZK, we kind of went over this, unless it's kind of like paired with another cryptographic primitive, might be a little bit difficult to use this. You could theoretically use FHE or like MPC, different type of scheme, kind of nested inside of it. It's always an option. And FHE right now, is a little bit slow, but the hardware I think is accelerating to some aspects. I mean, everyone says that we're gonna see an order of magnitude increase or whatever, and is it true? I mean, I don't know, but like that's what they say, and apparently that's there's a lot of stuff we've been working on, even at Phoenix, right? Like one of the things we're trying to integrate to is like the GPU integration, etc. Then I guess the FPGAs, ASICs, etc. The spiel. So like an FHE rollup is kind of useful in the aspect where, who doesn't like rollups, I guess, or maybe there's too many L2s, who knows, but it is what it is. So it's classic stuff, sequencers, orders and stuff. There's a slight different queue depending on like the nuances of the threshold network and like if you're calling a decryption and like how the operations are executed symbolically. But from a high level, you can kind of think that this is, the base version of this, I guess, is some sort of like optimistic verification. Like the post-execution validators can submit a challenge. We currently use a fork of like the Nitro prover. I kind of look at this as like, the computational overhead of the proof generation for like the actual FHE operations to verify state, like, instantly for instance settlement is like difficult to do, but, I think it's kind of things like verifiable ML or even like rollups when they first came out, right? Like the first ones are optimistic and you sort of move towards them and eventually maybe you get to sort of like Validium, etc. or ZK, depending on who you ask, I don't know. So from a high level, if you think about how the virtual machine works, like if you guys are familiar with the concept of like stylus, it sort of has like this intermediary interface between the EVM and like something for the operations for the FHE operations that we're currently using are written in Rust, right? And like you can't really run that just normal Solidity. It's gonna like there's overhead and it's expensive and like duh. But like, so basically you can kind of think of this as these interfaces sort of act as these like stateful precompiles that like when they're called upon, they will like execute the operations and then they will be verified in a format that the L1 in this case the Ethereum can validate. And so from this, we can move on to an example of more like symbolic execution. But I'll get to that a little bit more in a second. So the threshold decryption. So generally, like from a high level, when people are talking about FHE, usually each of these ciphertexts kind of need to be encrypted with a similar key or like a similar key set. So you can kind of think of like taking a single key, splitting it up amongst a few validators, and then requiring like I don't know, I want 3 or 4 for this thing or like whatever you want. And so this applies to decryptions, re-encryptions, and we'll get into like what a re-encryption is in a little bit, like a sealed output. But from a high level, this is using some sort of like MPC protocol to kind of reconstruct the shares, if this makes sense. I won't dive into too much here, but basically it's like you go through and you're like, okay, hey, we all want to be able to reconstruct this like secret. So like, how are we going to do it with that? Well, distributing the key. But this is something that is going to be developed in the in the very soon in terms of the next testnet. I guess like I think in like a week should be out for testing, and then the next one will probably be like a different version of it. But anyway, so yeah, just to wrap this up, this section of the kind of overview architecture, the fraud proofs are nothing too crazy. It's kind of like I was saying, using that WASM interpreter. That's if you think about it conceptually, sort of like the interface and like stylus. And so yeah, when it comes to these arbitration, it's standard optimistic verification in the sense where it's not the most efficient if someone actually ends up like attesting, but like how often does that really happen? I don't know. Maybe not really have an opinion on that, but like the FHE coprocessor is basically the concept of like the symbolic execution that I was talking about. Because realistically, who wants another fucking L2, right? There's too many L2s, liquidity, fragmenting, whatever. So I think the idea here is to like try to go towards the users, right? Like, hey, like this guy, I don't know, his uncle works for Base or some shit. He just really wants to work there. Like you just put it on there. So it's kind of like, in this aspect, you can think of it that you have the UN256s that basically are EVM native, and these kind of act as like pointers to the ciphertext. And then if you're adding like ciphertext A and ciphertext B, you're going to know which the handles, these hash values that represent where the ciphertexts are actually stored. And then when you run this operation, the operation itself is verified. How you do this verification process, I don't know how to say it's arbitrary, but there's options, right? So you can even use something like an eigenlayer AVS, which is like something we're doing, building at Phoenix. But anyways, so yeah, just kind of going over, if anybody is interested in building, I want to emphasize that like it's relatively straightforward to build a Phoenix. I mean, I hesitate to use that a little bit, but in the sense where it's just, if you know Solidity, it's relatively easy to pick up. As you can see, you kind of just import it as like a library here. You don't have to necessarily learn a new language or worry about like different like I guess client-side storage, etc., or communication, etc. in this case. So it is kind of nice in that aspect. There's local setup if you guys want to use hard hat. There's also a remix plugin for those of you that I don't prefer remix. I mean, I don't say that pejoratively. Like I kind of fuck with remix. And then there's Foundry. I think a lot of more developers are kind of using Foundry now. I guess it's cool, it's hip. It's like I don't know, it's the Gen Alpha. So inputs. So I like to think about when you're working with FHE, it's sort of like try to not change too many things from how you're normally developing with Solidity. So usually if you use like a UN8, for example, right, like an unsigned integer 8-bit length representing a number from like 0 to 255. So you could use this for arbitrary bit length, 1632, etc. But basically it's going to work in the state of your contract similarly to if you're going to add these numbers, you're going to subtract these numbers, you're going to let's say you want to use it as like a value in a key mapping pair, etc., things like that to represent an ID or a balance. If a really simple example, if you wanted to use like some sort of encrypted token, private token, right? It's basically just have an address that maps to a ciphertext value. That ciphertext value represents your balance, etc. So basically we have this new data type that's called an EUN, arbitrary bit length, but like basically it's kind of how you're putting in this number. So like if you were to look at like I guess like the call data or whatever, the input params of your function, however it's verified, right? You're just gonna see a ciphertext blob, so people are gonna see what number you put in. But you can also just raw dog it with like arbitrary with general bytecode too, if you prefer that. I guess if it just makes more sense with your logic, or if you just prefer it, yeah. So what I would say the one tricky thing with like working with FHE here is that kind of works like constant time code. Maybe some of you that have worked with like similar things, like certain type of circuit DSLs or whatever, like might be familiar with this. But basically you're using a selector function here. So I'm sure we're all familiar with like the left side pad syntax. It's like basic stuff. If else, well, that doesn't really work because you can't have like these branches because they're both going to execute, etc. So I like to think about it in FHE, there's conditional assignment, but there's not conditional write. Basically, both branches are going to execute, but what it gets assigned to, that's what's indeterministic or like deterministic. Based on your equal. So like if you look at this, you're basically checking if A is less than B, and then you are assigning that to an equal, and equal is exactly what it sounds like. It's equal, it's 0, 1. And basically from there it kind of branches, diverges into either A or B, so if you can assign it that way. So I admit it's a little bit annoying and like to have to work with, but it's just sort of one of the I guess design constraints of our time. Require statements are pretty straightforward. It's basically just like if you use an EVM require statement, except this way you're actually checking to see if like the FHE value is like the encrypted value is like you don't want someone sending like 100 tokens if they don't have 100 tokens, it's going to fuck everything up. So one of the things to check, you have to be cognizant of the fact that this is going to leak. I mean, it's going to be a conditional like Boolean leak. Like basically, did it not? You can brute force it in some aspects. So it's just a design constraint that you have to be aware of in terms of avoiding leaking information. Talking about leaking information, conversion leakage is one of those things that like generally speaking, you want to avoid leaking plain text to memory. Once you have plain text to memory, that's where a lot of attacks happen, right? Man in the middle attacks, etc., database code, whatever. Especially when we're working with something like an EVM, which is kind of like this, like the whole stack trace is going to be available, right? It's public, it's every state change is recorded in something, etc., validated, etc. So you have to be very careful. Here's an example where you're basically putting in like an unencrypted integer, and then you're basically trying to encrypt it in this case, but you're going to see what the encrypted integer was, right? Because it's in plain text. So you have to think about this is going to leak somewhere and it could fuck everything up because like, you build state from this and then sometimes you just get rugged. So like, no, I see what you did. And so Phoenix.js is like kind of the JavaScript library. I guess we all probably kind of hate JavaScript, but it's just one of those things where you kind of got to work with it in some aspects, I guess, when you're building out your client, right? So, but it's not too different, I like to think, especially when you think about, for those of you who maybe worked with like Ethers.js, for example, it's not too different. So you're basically just integrating your API. You have like this one extra step here where you're basically encrypted the number 5s and EU and 8. And then that like data type, that blob, whatever you want to call it, the bytes, if you want to just raw dog it, you can just put that in too. But yeah, so that's basically what you're going to put into the input as your function. So in that aspect, it's not too different from what you're normally used to doing for, I guess, full stack Web3 developers. Permissions are basically like, you can kind of think of these as like the view functions in FHE, like restricting like who's allowed to see what, like, like if I have like I don't know, like an OnlyFans or something, and I don't want people getting a free look at my body. You can basically make so only people that like pay for it are able to, get the sealed output of it. So you can kind of think of this as like you're basically doing a stateless decryption, and you're wrapping it towards the user's pub key, and then you send it to them. That is what's returned to the client. Once the client gets that locally, you can basically unwrap it using your secret key. And so in this aspect, it's sort of like the view function in that aspect, and it can be permission conditional. Speaking about adding extra conditions, this is how you can do it in your contract. Like I said, basically it's like only the premium subscribers get to see like this week's like new leaks or news or whatever. So you can basically make it conditional. I don't know why I used OnlyFans, but like I guess you could use it for like professional stuff. Like you pay for subscription to some sort of auditing service, and then you get the results, etc. So I'm just kind of wrapping this up with this smart contract example, just trying to emphasize how it's relatively straightforward in the aspect of it's like, yeah, you just have to use native solidity. The data types might take a little bit to wrap your head around, but like generally speaking, it's not anything too different. General runtime tips, if you're like, okay, hey, FHE is expensive, it's kind of slow, why the fuck isn't this shit running? Why am I getting an overflow? Well, could break up your transaction. Also, you have to be cognizant of the fact that the operation that you're doing is going to make a difference, and the bit length that you're operating on is also going to make a difference. Relatively straightforward, intuitive. Like adding 2 numbers should be cheaper than dividing 2 numbers, and like adding 2 8-bit numbers should be cheaper than adding like 2 16-bit numbers. So nothing crazy. The other thing too is like, if you guys are interested in working on these contracts, like ChatGPT is actually like kind of based, like, you might think like, oh hey, is it trained on this? Is it going to give me some dog shit that's not going to compile? It's like, yeah, it's okay. I don't know, give it a shot maybe. And so for those of you that are interested, this is a good way of getting started. With our current testnet, although we are moving over to a new testnet, I'm going to miss chain ID boobies, so it'll be a thing, or 808, I don't know why I said that, but and that's on my Telegram if anyone wants to message me or do whatever. So thanks for your time.
Thank you very much, Kyle. Koshiyama from Phoenix. Wow, thank you very much for being with us. Very efficient as well in terms of your speech. And thank you so much for shedding light on the FHE and its application. Yeah, so any last final message to the audience?
I don't know, are there any questions?
Okay.
Okay, I'm not answering questions. Yeah, thanks.
Okay, very short and concise. Thank you very much, Kyle.